All right, today we're diving headfirst into the world of extreme speed. And I mean extreme. We're talking about a technology that could totally change travel, defense, pretty much everything. The Scramjet. And our guide on this journey is an incredible thesis on hypersonic engine design by Kristen Nicole Roberts. So let's get into it. To start, I just want you to think about this one question. Seriously, picture it. You're trying to light a match in a hurricane. Now, imagine that hurricane is moving at thousands of miles an hour and it's inside a jet engine. That, right there, is the absolutely mind-bending challenge of hypersonic flight.
We're not just talking about going fast, we're talking about speeds above Mach 5. That's over 3,800 miles per hour. To put that in perspective, you could fly from New York to Los Angeles in under 45 minutes. But to do that, you need a whole new way of thinking about how engines work.
To really get why scramjets are so revolutionary, we first have to talk about a speed limit. See, the conventional jet engines on the planes we fly on today, they can only go so fast before they just give up. This really breaks down the evolution of jet engines perfectly. You start with a regular turbojet, right? It uses fans to squish the air. Then you have a ramjet, which is a step up. It uses its own forward speed to compress the air, but, and this is key, it still has to slow that air way down to below the speed of sound to burn the fuel. But the scramjet? Oh, the scramjet does something that sounds impossible. It burns its fuel in air that is still moving at supersonic speeds.
So why can't a ramjet just keep going faster and faster? Well, here's the problem. Trying to slow down air that's moving at hypersonic speeds is like slamming on the brakes at 4,000 miles an hour. The friction, the pressure, it generates so much heat it would literally melt a normal engine from the inside out. The laws of physics just hit a hard wall. So if you can't slow the air down, what do? Well, you stop fighting the speed. You build an engine that is designed to embrace that raw, chaotic, untamed velocity. And that is where the scramjet comes in.
And here it is. The name tells you everything you need to know. A supersonic combustion ramjet. It's an engine that's literally built from the ground up to do one thing: achieve stable combustion in air that's moving faster than sound. It's a true marvel of engineering. And this, right here, is the fundamental genius of the whole concept. It doesn't fight the hypersonic airflow, it works with it. The entire shape of the engine is designed to harness that velocity, to use the shockwaves to compress the air just enough and turn that extreme environment into an advantage. But working with that speed, well, that brings us right back to our original problem, doesn't it? The match in a hurricane. So let's take a look at the specific nuts and bolts challenges you have to solve to make this thing actually work. This diagram from the research is just fantastic because it lays out all the core issues so clearly. It's like a roadmap of all the engineering headaches, from getting the air in to the combustion itself, and even the basic materials you need to build the thing so it doesn't just tear itself apart. Okay, let's zoom in on the heart of the engine, the combustor. The very first massive hurdle is simply getting the fuel to mix with the air in the first place. I want you to try and wrap your head around this. The air is screaming through the engine so fast that the entire process, injecting the fuel, getting it to mix properly with the oxygen, and then actually igniting it, all of that has to happen in less than 1,000th of a second. If you blink, you've missed it hundreds of times over. It's unbelievable. Okay, but let's say you do it. You solve the combustion problem. Now you have to make sure the engine doesn't just vaporize itself in the process. And that brings us to the second huge challenge: the heat. We are talking about temperatures inside a working scramjet that can reach levels hotter than the surface of the sun. Seriously. So just finding materials that can take that kind of punishment while also being light enough to actually fly is one of the toughest puzzles in all of material science. Now, what's so cool about the thesis we're using as our guide is that it doesn't just talk about the problems. It gets into the nitty-gritty of solving them. Specifically, Kristen Roberts' work focuses on designing a scramjet that can start operating at Mach 4. And this quote right here really frames just how important this kind of work is. This isn't just a theoretical exercise. It's about pushing the boundaries of what's possible, stretching the speed range where these engines can actually work, which is absolutely vital if we ever want to make them practical. So, if you're the engineer sitting down with a blank sheet of paper, where do you even start? Well, you start with the most fundamental choice of all, your fuel. What are you going to use to power this beast? The research really breaks down the two main options.
On one side, you have hydrogen, and on the other, you have more traditional hydrocarbon fuels, kind of like jet fuel. And as the data shows, there's a very clear set of pros and cons for each. So you see the dilemma, right? Hydrogen is amazing. It burns super fast, packs a ton of energy. But it's not dense at all, which means you need huge, bulky tanks to store enough of it. Hydrocarbons, on the other hand, are dense, storable, easy to handle, but they're slow to burn and ignite, which is a huge problem when you only have a millisecond to work with. It's a classic engineering trade-off. Okay, so you've picked a fuel. Next up on the checklist, you have to manage that insane airflow. The front of the engine, what's called the inlet, has to somehow compress that hypersonic air just enough to make combustion even possible. So how do you do that efficiently? This part is just brilliant. The design basically uses these carefully angled surfaces to create shockwaves, and those shockwaves do the work of compressing the air. Now, looking at the data from the thesis, an inlet designed to create 3 shockwaves gets you about 92% efficiency. Pretty good. But check this out. Add just one more shockwave to the design, and the efficiency jumps to 95%. That is a huge performance boost from a seemingly small design change. So, after walking through all this incredibly complex engineering, why does it all matter? I mean, what's the payoff? Well, solving these challenges isn't just some academic game. It unlocks a future of transportation that honestly feels like it's straight out of science fiction. I mean, just look at the potential here. You're talking about hypersonic cruise missiles that are so fast they're nearly impossible to intercept. You're talking about spacecraft that can take off from a runway, flies straight to orbit, and then land again, which would completely change the economics of space travel. And of course, the big one, high-speed passenger planes that could connect continents in just a few hours. The kind of research we've looked at today is such a critical step in making that future a reality. It proves that with clever design and a really deep understanding of the physics, these seemingly impossible problems of hypersonic flight, they can be solved piece by piece. The question really isn't if we can achieve hypersonic travel anymore, it's about how we perfect it and what that biggest final hurdle is that we still have left to overcome.